This is my pleasure to introduce the plenary speaker, Nizar Touzi, with my colleague at École Polytechnique. And actually, there's probably no need to introduce Nizar because he's one of the most famous researchers in quantitative finance. He made a lot of contribution in PDE, stochastic control, financial modeling, principal agent problem, exact simulation of processes, optimal transport. And today Nizar is going to talk about continuous time principal agent and optimal planning.
Thank you, Mathieu. So my talk is about continuous time principal agent problem. And I will start by explaining, for those who are not familiar with this problem, what is the context of this problem, and then show you that some general solution that we came up with a few years ago with Dilan Kosamai and Yaksha Svitanich, who are both present here in the audience, and then make the connection with the so-called optimal planning problem, which turns out to be connected to this one. And well, for me, this problem was, I discovered this problem thanks to Yaksha. And it was a great pleasure because this problem connected many lives, different lives that I had with Dilan as well. We had different lives, and suddenly with this problem, they came up together. Okay, so let me quickly explain what we are talking about. So the principal agent problem is the simplest problem which introduces incentive theory in economics modeling. So we want to introduce incentives between a manager who delegates the management of some output and who wants to incentivize the agent, the second agent wants to incentivize the agent so that the agent works in the benefit of the manager while being happy, while maximizing his own interest. So this is incentive theory. So the story is in this slide. So I'm denoting by X the output process, which is not a process so far. X is the value of the output that is managed by the agent, and the agent dedicates an amount of effort, which I denote A in this slide, and by dedicating this amount of effort, he's able to change the distribution of X, because only distributions will be important in all the criteria. So we'll change the distribution of X from X to XA, X parameterized by A. So later on, we'll be in continuous time, this will be a controlled process. So, of course, the agent will choose his optimal effort according to the optimization of some criterion, expected utility of something. In this something, there is we will feel this right away, but before, there is a cost for this effort. So C of A is an increasing function of A, and so devoting the effort A is costly. So how much am I willing to devote effort, given that the cost is given by C of A? And there's a minus sign, so if I stop here, then maximizing increasing function, utility function with a minus sign, I would devote the least possible effort, which would be a catastrophic situation for the principal. So because of that, you have to put something here, which would be the salary. If you put as a salary any constant as big as you want, the result will be the same, because this is a constant and the agent will end up minimizing the effort. So the only way to incentivize the agent and to push him to do something else than minimizing the cost of the effort is to index the salary on the production asset. And this is, of course, an old idea. So suddenly, by defining the salary as a function of the production asset, you see that in the maximization of the criterion of the agent, not only the cost of the effort is important, now there is a balance between the cost of effort and how much would I gain from my good management of the output. And the beautiful feature of this principal agent problem is that there's a second stage of optimization, and the second stage of optimization is done by the principal. Once the agent maximizes the criterion which is written here, then the agent returns an optimal response function a hat of c. So if you give me this contract c, this is how much effort I am willing to devote for the management of this production asset. And now, given this optimal response, a hat of c, then the principal can maximize its own objective, optimize its own objective, by choosing optimally the contract. What is the best contract from the point of view of the principal? Now there is one more constraint to add, is that we require that the agent be happy with this contract, because without this constraint, you see that what happens if you don't have this constraint, then the principal may choose c equals minus 10 to the 18, which means that the agent not only is going to work, but also is going to pay the principal negative salary. And the poor agent, if we don't put this constraint, has no choice but returning an optimal response to this negative salary, which would be, of course, typically very bad. But this would be catastrophic because from the point of view of the formulation of the problem, the principal would take utility, would benefit from the negative salary instead of the management of the own economic good. So we don't want this situation. So in economics, there is this participation, so-called participation constraint, which restricts the principal to propose contracts which provide the agent a satisfaction greater than some level of satisfaction rho. Okay? So this is a problem, two optimization problems. First, the agent optimizes given the contract C, returns an optimal response. Then given the optimal response, the principal searches for the best contract so as to maximize its preferences under the participation constraint. So this is a non-zero sum Stackelberg game, and which is typically in this form in one period is not so easy to solve, in fact. And it turns out that it's what I will show is that by going to continuous time, this problem is going to be solvable much easier. There will be an easy solution. Well, the intuition is that in continuous time we take benefit of the differential calculus in the time direction. This is what happens, for example, for Black-Scholes formula. Black-Scholes formula is much simpler than the binomial formula. Nobody wants to look at the binomial formula with the combinatorics, etc. Everybody is happy by the concentrated formula of Black-Scholes, where you have a clear effect of the parameters, etc. Okay, so continuous time. So my next slide will be a copy of this one, except that we are going to move everything in continuous time. So it will look ugly because there will be more notations, but in fact it's mimicking this slide, but by using optimization in continuous time. Okay, so now the agent is the guy who works. The principal is the boss. Huh? And now the controlled output is this controlled process. Control is new T. It's a control process. If you want to be precise, you have to take the control problem in its weak formulation, and there are good reasons for that from the economic point of view, but also from the mathematical point of view. So this is my output process, and by choosing the control nu, the effort nu, in terms of incentive theory, nu is the effort. By choosing effort nu, the agent is capable to change the distribution, to control the distribution of x, of this output process. And now I would like to present, in this continuous time situation, the following generality. So the contract stipulates 3 items. The contract consists of 3 items. The first one is a retirement time, tau. Tau, that's a stopping time. So in the beginning of the contract, you would be told that you would be pushed out at the age of 65, or if the output of the company is below some level because the company would go bankrupt. The tau can be a function of the output itself. So that's a retirement time. It is announced in the contract. And also some continuous payment, which I call pi. So this is how much, this is the salary. And there is the payment at retirement, sort of bonus that you get at the retirement, which I call xi. It's an f tau, measurable random variable, so it depends on the information at time tau. And given such a contract, C, with these 3 items, now the agent problem is to maximize preferences as before, and to return the optimal effort. Now maximizing preferences, the effort is new, choosing new is the same as choosing the distribution of X. This is why I'm writing it as a soup over probability measures on the set of paths. Now what happens to the agent gets a salary xi of X at time tau. This is part of the contract. And then up to time tau, up to the retirement time tau, gets continuous payment by t, but suffers from the cost of effort. So it's exactly a similar story to what we had in the previous slide. And then we have the set of acceptable contracts. So these are contracts for which provide the agent with a utility which is greater than some prescribed level rho. And now the principal problem is to choose optimally the contract. Choose optimally this set of 3 items, tau, pi, and xi, so as to maximize, given the optimal response p star of c. Again, exactly as in the previous slide. So given the optimal response p star of c, what is my best contract? Where you see that the payment comes with a minus here. Whatever I pay to the agent plus here becomes a minus here. And then there's a liquidation function of x. L of x is just a function which maps the set of paths into scalars, because we want to maximize something at the end. Okay, so it's exactly copying the slide from before, except that now we have the formulation of stochastic control. Okay, any questions so far on the model? I think some people in the room are very familiar with this. Maybe others are not. So the difficulty here, of course, is that we have 2 control problems which are strongly interacting with each other. And in particular, the second one is not so nice in the sense that it is highly nonlinear. It depends on the optimal response of the problem, of the first problem of the agent. And also with a constraint which is not so nice. The constraint is highly nonlinear. The A of C greater than rho. And in fact, it's even worse because it's in feedback formulation, so technically it's not so nice to work in that setting. But in fact, there is an easy solution. So let me show you how to solve this class of problems. There is a general recipe. So first, before going to the general recipe, we have a restriction. Whatever I'm going to tell you works only, so watch out the B here. The dynamics of the X, there is a restriction that the drift, the controlled drift, the B of X and nu, has to be in the range of the diffusion matrix, of the controlled diffusion. So for example, if sigma equals 0, my solution will not work anymore. If sigma equals 0, everything should be constant. Degenerate systems are not, we cannot handle degenerate systems with this methodology. So we need some randomness somehow. The sigma is a non-degeneracy condition. Sigma can degenerate in this form, but cannot degenerate just like this. If sigma degenerates, then the lambda has to do something similar. So lambda has to be B has to be in the range of sigma, sorry. Okay, so the general recipe is to introduce the so-called Hamiltonian for the agent problem. So for those who are familiar with stochastic control, you know that if you are given a control problem in this form, you have to write the Hamiltonian. And the Hamiltonian is just multiplying the drift, control drift by the gradient, plus 1/2 sigma square trace with the Hessian, minus or plus the integral cost function. And I did not put any discounting here. Even if there is discounting, you can also account for that. So in the present setting, the Hamiltonian is exactly of this form. So the drift, control drift, times the gradient. So Z will stand for the gradient. 1/2 sigma square traced with the Hessian. So gamma is a matrix of the dimensionality of the Hessian. And this is the integral cost minus Ct plus Pt. Pt is the continuous payment. Okay, and the Hamiltonian consists in maximizing. The definition of Hamiltonian is to maximize over all controls this quantity. So we are all used, for those who have taken a course on stochastic control, we are used to this Hamiltonian because this is the key to write the so-called Hamilton-Jacobi-Bellman equation. But Hamilton-Jacobi-Bellman equation is in Markovian problems. Here it's not Markovian. It's not Markovian for many reasons. It's not Markovian because I decided to put everything depending on the path, on the whole path. But the main non-Markovian feature is the Xi of x. Is because from the economic point of view, we would like that the payment function depends on the whole path. Doesn't make sense. There's no reason to restrict to the output process just at the very end. You're not going to be paid as an agent only upon the state of the output process exactly at the end. You would better be paid upon the whole trajectory. So because of this, and this is changing completely the problem, in fact. No? If you restrict C to be Markovian, C to be a function of X capital T, then it's a different problem. So by allowing for C depending on trajectory, then this problem now is path dependent. So in principle, you cannot write the AJB equation. It's not Markovian. So the first reaction is to panic, is to say, this is more difficult than AJB. AJB is already difficult. But in fact, it makes it easier. To allow for path dependent C will make it easier. And I will now explain why. Okay, so forget about path dependency. Let me define the Hamiltonian exactly as in the Markovian theory. So now it depends on the path, Hg of omega. Okay, it's not a problem. I define H like this. Now, second definition. Second definition is for any initial condition y0, any process z, any process gamma. Define this stochastic integrals. Yt z gamma is initial value y0, which is chosen arbitrarily, integral of z dx, which is chosen arbitrarily because z is chosen. Then same thing for this integration of gamma with respect to the quadratic variation of the process x, and minus Hamiltonian, minus this Hamiltonian. So we use this h here in the definition of y. And importantly, I would like these stochastic integrals to be well defined, P almost surely for all P in my admissible dynamics. So P script, remember P script was the set of all probability measures that I can reach by controlling these dynamics. That's P script. So what I'm imposing here is that these stochastic integrals are defined P almost surely, so it depends on some full measure set. And what I want here is that these things be defined somehow uniformly with respect to all these measures, which might be singular because the volatility, the diffusion process is controlled. Okay, so these are two definitions. You define the Hamiltonian, then you define this process y, and then you can prove this very easy result. This one is very easy because the proof is just a classical verification argument in stochastic control. It's a few lines, 3 or 4 lines maximum. What is this saying? This is saying, remember my notation dA of C. My notation was dA of C. Let me go back. This is the agent problem, dA parameterized by the contract. And the contract has 3 items, tau, pi, and xi. Xi is the payment at retirement. So this first result says that for any tau, any pi, if you choose as a xi